Hello friends, in this lecture we are going to deal with the Dirac's equation for hydrogen atom and we'll try and understand the grand success of the relativistic quantum mechanics part established by Dirac in this video lecture. Now that here we shall roll through the Dirac's equation in a very settled approach which is followed by most of the authors. Dirac's solution for hydrogen atom, where we are going to consider not only electron but a proton associated with it, and we are going to add a potential energy term for a single proton electron configuration, and then we'll compare Schrodinger's and Dirac's uh, energy equations for hydrogen atom, and then we shall focus more on Dirac's equation predictions. So let us begin our discussion. I am your instructor, Professor Shyamkant Anwane, associated with Science College, Nagpur, India. In this lecture also, I have a very high temptation of re-deriving this Dirac's equation, but very quickly in a very subtle mathematical way, wherein I am starting this with relativistic energy equation of a particle E square is equal to Pc whole square plus mc square squared, where mass m is rest mass m0. For writing convenience, I am just considering m. Now, if you take square root of this equation, energy is Hamiltonian. So I have replaced E by h, and mc square I have taken common from the square root, and we are left with 1 plus p square upon m square c square. This term is less than unity, and the binomial expansion of this we shall consider. It will have infinite terms. The term here you can call p square by m square c square will appear here. In the next term it will be square of this term, so on and so forth. So it will be small. This is not a good way of writing Hamiltonian, and solving will be difficult because it carries infinite terms. But however, we are looking at this equation to understand what Dirac's idea was actually, to not go for such critical Hamiltonian which will turn to be unsolvable and unprofitable to handle that. So expanding this bracket, we are having a rest term, rest mass energy. Then we are having p square by 2m. This resembles with kinetic energy. So the original Hamiltonian you can call. And these terms are relativistic corrections. Fine. We are going really a step ahead with this approach. Now my objective is this E square is equal to p square c square plus m square c to the power 4. This a square plus b square I am writing, and this I am trying to write as a plus b whole square, kind of. So most linear expansion of this pc can be some constant alpha times p. Momentum is a vector operator, so I am considering kind of vector such that alpha 1 p1, alpha 2 p2, alpha 3 p3, where p1, p2, p3 are simply momentum along x, y, and z direction. They can be used in the operator form we have seen. And here we have introduced another constant beta with the rest energy. Now, with this, what restrictions we need if we square this, or rather if we open this square, we need alpha 1 square equal to alpha 2 square equal to alpha 3 square equal to beta square equal to 1, so that we'll be getting this pc whole square plus mc square squared. So the inducted constants alpha and beta should disappear. Moreover, in this expansion we'll be getting 12 more terms. Those should vanish. For that, for all I not equal to j, alpha I alpha j plus alpha j alpha I should vanish. Similarly, all alphas, that is alpha I beta plus beta alpha I for all I, it should also vanish, so that this takes care of 12 terms that should vanish. And in turn, we are in position to get something very interesting. But alpha and beta cannot be normal numbers. If we take 3 into 4 plus 4 into 3, it can never be 0. So Dirac's approach was to consider a 4 by 4 matrix composed of Pauli's 2 by 2 matrix, this sigma I, where you can consider sigma 1, sigma 2, sigma 3, or sigma x, sigma y, sigma z, 3 Pauli's matrices. This bold 0 is 2 by 2 zero matrix, that is 0, 0, 0, 0. And beta is equal to I 0, 0, I, that is identity matrix 1, 0, 0, 1. So this I is 2 by 2, this bold 0 is 2 by 2. So here we can write the Dirac's equation in the operator form as appearing on your screen. We have considered solution of this also. We'll begin with that in the next slide. In relativistic quantum mechanics also, like in non-relativistic quantum mechanics, it is perceived that electron is in the different spin state for stationary observer and the one moving with the electron. The non-relativistic Schrodinger's equation is that the one which can be solved analytically for hydrogen atom, and it predicts the energy levels that are closely in agreement with what we observe. Naturally, physicists were motivated to look at the Dirac's equations predictions for hydrogen. In addition of the potential energy term that describes electron moving in the presence of proton. In our natural units, this takes a form with minus alpha over r times wave function. Here r is the distance between proton and electron, and alpha is so-called fine structure constant, which is approximately 1 over 137. For a free electron, the total angular momentum J is conserved, but orbital and spin angular momenta are independently not conserved. This form of Dirac's equation can be solved analytically, although it's more complicated process than the corresponding Schrodinger's case. The solutions are described by three quantum numbers n, j, m sub j, which is appearing on your screen. N largely specifies the energy level. You can observe here. N is equal to 1, 2, 3, and so on. J specifies the total angular momentum and also slightly affects the energy. It takes values 1 by 2, 3 by 2, 5 by 2, and so on up to n minus 1 by 2. Mj specifies the z component of the angular momentum. It takes all values from minus j to plus j, including 0. In fact, minus j, then minus j plus 1, and so on up to plus j. Before we look at the Dirac's equation predictions for hydrogen atom, recall it that had a long been known that hydrogen spectrum has so-called fine structure. Schrodinger's equation predicts the same for energy levels for orbitals of types s, p, d, corresponding to the same value n. In addition to the principal quantum number n, the energy explicitly depends on the angular momentum, that is total angular momentum j. It's helpful to expand this into a series of decreasing terms that you can see on your screen. The first term m is simply intrinsic energy of an electron. Remember that in our units the speed of light c is unity, so this corresponds to mc squared. The second term is identical to the Schrodinger's energy level. You can see on your screen m alpha square upon twice n square, and this depends only upon the principal quantum number n. The next term is where the angular momentum quantum number j plays a role that corresponds to the fine structure. The predicted energy split for n equal to 2 and j equal to 1 by 2 and 3 by 2 we will specify in the next slide. As I said, Schrodinger's equation predicts identical energy levels for all orbitals, say like s, p, d and so on, that corresponds to the same principal quantum number n. However, in practice, all orbital types except s orbital are observed to split into two very closely spaced energy levels. You can observe here. So here you can see the splitting is fairly close, that is accurately predicted by Dirac's equation. So here you can see the predicted energy split for n equal to 2, j equal to 1 by 2 and 3 by 2. The energy difference E2, 3 by 2 minus E2, 1 by 2. This tiny amounts to a 0.00004535 electron volts. This is in excellent agreement with the observed fine structure split. So the Dirac's equation actually predicts the energy difference between a 2p orbital with aligned orbital and spin angular momenta and 2p orbital with opposed orbital and spin angular momenta. Here on this slide you can see the schematic representation of magnetic momenta because of S and L corresponding to 2s and 2p orbital. In the video on hydrogen, we looked at the structure of hydrogen orbitals as predicted by Schrodinger's equation. Just as Dirac and Schrodinger equations predict energy levels differing by only tiny amounts, they also predict electron probability distributions that are practically indistinguishable. Let's look at the ground state 1s wave function. These are two solutions actually. The Schrodinger's solution is e to the power minus r. There are two such Dirac solutions appearing on your screen which are having opposite spin. These have the same energy but different spinors. Note that for compactness we don't show the time dependence factor here. The radius r is measured in the units of Bohr radius. Alpha is a fine structure constant. Here you can observe gamma to be square root of 1 minus alpha square, and alpha we have already discussed, it's 1 upon 137. Now if you consider 1 minus gamma, it is a very small number you can observe on your screen, and that is appearing in the down spinor of the wave function. If it were 0, then this would be identical to Schrodinger's solution with a spinor for either spin up or spin down. So the Dirac's equation predicts spin 1/2 properties of electrons and accurately describes the fine structure of hydrogen. These are the monumental accomplishments that strongly suggests that the Dirac's equation is on the right track. But when you are taking square root of energy, you have plus and minus root. So there are those negative energy states. They are a deal breaker. And they not only seem non-physical, they also lead to impossible predictions. Dirac has a very strong faith in his equation, and he was insisting that this negative must have some meaning that should not be ignored. So in the next lecture, we shall try and understand what was Dirac's explanation, the course of his thinking through the research papers we can track, and what was the final explanation, and was there any experimental evidence. I want to quench your curiosity by making a statement that after Dirac's theory, after 6-7 years of his theory, there was the first experimental proof to the negative part that was appearing in the equation when we take square root of the relativistic energy equation E square equal to P square C square plus M square C to the power 4. So in the next lecture we shall address this issue.